It's a good question. I don't quite remember because we had three parallel things going on at the same time. Probably the first experiment, at least the first one we published, was the one with the multiple spin echoes to get a single shot 2D spectrums, just like Lucio Friedman is doing now. So multiple echoes and stitching them together and making a 2D spectrum out of it. At the time was to get a two-dimensional J spectrum. It was a pretty useless experiment really, because who needs J spectra? But technologically it was very difficult. We could do it on a new spectrometer that had been built in the group that I was sort of part of. And that was one of them. And the other one that I was more proud of, but probably came second after I visited the group of Guthrie, and I met Kuniyuki Nagayama, and he explained to us the projection reconstruction theorem on why you wouldn't be able to get an absorption mode homonuclear decoupled spectrum. And I felt very bad that me being a physicist, I hadn't realized, and of course he was right, mathematics is very clear cut and very simple, and that we had totally missed that. So then I came up with this constant time trick, as it is. So constant time spectroscopy was actually basically a rebuttal towards Nagayama for, hey, we can make homonuclear decoupled spectra by doing a constant time experiment. So that was probably my proudest, happiest moment, that I sort of was able to sort of at least save face and be able to do something that hadn't been done before. Again, this is a very difficult question. I had so many favorite projects that I've worked on over the years. We had magic angle hopping, magic angle flipping in the solid state lab, working with Gary Mashel and Nick Severini. It was fantastic. That involved some engineering. And in the subsequent stuff, the development of the triple resonance experiments, again, involved a mix of building equipment, because the Bruker spectrometer at the time was totally ill-suited for doing that. So that was fun, but probably, maybe because my memory isn't, you get older, you don't remember as well. The most exciting experiments are the ones I'm doing right now with the pressure jump NMR. I really love those. It's again a mix of hardware, software, and some application to a real life problem, protein folding. Again, you can't get successful just by being smart alone. You got to get lucky too. And I think in my case, getting lucky was the key to the success. I mean, I got lucky by being adopted in the Ray Freeman group for 3 years to do my PhD effectively as a guest worker in this group. And it was a fantastic experience. Being in a room, the same room with Malcolm Levitt, James Keeler, Ola Sørensen, AJ Shaka. We were all stuck in this small room. We drank tea and coffee together. So that was laid the groundwork. So that was the first case of luck. The second case of luck was when I moved to Colorado, where I met Nick Severini. We got to do this fantastic solid state NMR experiments. And that involved tinkering, and Nick was very good at it. And I got lucky again when I went to the NIH. I never really had my eyes set on working for the government, but ending up there, I mean, there was money, I could do stuff that I wanted to do. Nobody would ask me ahead of time, is this worthwhile doing? Of course, we've got the retrospective evaluation, but as long as you had done something useful in the past 4 years, you're going to get money for the next 4 years. So when we wanted to do triple resonance, and it was obvious it was going to be useful, working with Dennis Torsha, Dennis explained to me that working with isotopically labeled protein wasn't really cheating. Other people said, no, you got to work with natural proteins derived from fish or cattle or whatever. But Dennis explained to me, and Dennis is a physicist as well, and he was very convincing. 10 years from now, everybody's going to be working with cloned proteins. And then I realized we can use all the small molecule experiments on isotopically labeled proteins. So this was fantastic. Gave us the chance to really develop this technology, develop three-dimensional NMR. And when we did this, we tried to get it published. The attitude was very negative. And they looked at us like, we don't need three-dimensional NMR, and it's going to be too expensive. So imagine if I would have gone out and been at a university, applied for a grant. They say, that's not worth funding. And that's even before we've done it. After we've done it, one of the referee reports said, can't be true because it's too complicated. And the other one said, well, maybe true, but we can't afford it because glucose is so expensive. So imagine applying for a grant to develop this technology. It would have been totally non-fundable. So being at the NIH has been really very fortuitous for me. I tell my students and postdocs, you know, this is your chance. You want to have a successful life in science. This is the moment in your career. You got to grab it with both hands and go for it. Because if you get a faculty position, you're going to have all the administrative hassles, you got all the other things to worry about, you're going to have a family, you're going to have, right? Now is the time you can actually live your heart out in the lab, work as hard as you can on whatever you find interesting. Pursue it, and this is your gamble. You got to take it, and you got to go 100%. Otherwise, it's just not worth doing. You're never going to get anywhere with three-quarter pressure. Actually, I wouldn't be able to just do science and NMR all day long. I really need a break every day, and one of the things I like to do is athletic sports. I used to be very active in rowing, and I hurt my back, so now I'm back in cycling. I used to race bikes when I was in grad school, and undergrad actually. I got back into that about a dozen years ago, and I still ride every day about 25-30 miles with a group. So we go for lunch, and an hour and 5 minutes later we come back, totally sweaty, tired, hungry, but back in the lab. And if I wouldn't be able to do that, I wouldn't be able to keep focused all day long. It's again a very difficult question because I got lucky quite a few times. I'd say the luckiest one, probably because, again, my memory is not so great, is the last one that I'm excited about, is this pressure jump NMR. It's really working fantastic. But we got lucky so many times. Early on, doing the HMBC experiment, for example, which was essentially a trivial experiment, like for small molecules. And conceptually, it was obvious this was going to work. But that this was really going to be that big, again, people refused to believe, and it worked so nicely, and it was obvious thinking about it. This was working with Michael Summers at the time. He had a good problem, and again, from that sense, a lucky experiment. He came with this vitamin B12 and questioning the assignments, and I told him, well, the easy way to do it is if we do this experiment, this HMQC with long dephasing delays, and guaranteed you're going to see those connectivities, and that will be the end of it. So you could call it a lucky experiment. Certainly not intellectually challenging, but turned out to be very practical for organic chemistry. That's an interesting question. Probably that dates back to the mid-80s. The Gordon Conference, and I was still young, of course, nobody, sitting in the back. In the front row, we had Abraham, John Wall, Jean Giner, Schlichter, and those guys, they had sort of like a pecking order, and it was interesting. They actually got nervous. Alex Pines was there, Alex was nervous, John Wall was nervous, and that's hard to imagine. Seeing to us, those guys were like the gods, but it was obvious that they were looking at one another for a sign of approval. And it was for us as young guys to see those absolute stunning, super intelligent guys still being nervous, looking at one another for approval, was, to me, was mind-boggling. Well, by now I'm almost an old guy, you know. I mean, I feel like I'm still young, but I'm in my 60s. I've got a great project going on, so I want to keep working on that. There's so much these pressure jump experiments that we're doing. We have at least 10 years worth of work left, of new things to do. At the same time, we've got a lot of important work going on in more conventional NMR that needs to get finished. So even if I wanted to, I don't think I could afford switching to yet something else. No, there's so much low-hanging fruit that I'm enthusiastic about. I have no need, no reason, no desire to actually switch to something that I'm no good at. So I'm going to stick with it. Again, a great question. There's so much exciting work going on. Just this meeting here at the EUROMAR, it's amazing. I can't go, it's too bad there are parallel sessions because I'd like to split myself and go to 2 or 3 sessions at the same time. There's fantastic work. There's decoupled GPCR work that's going on, the fast imaging experiments that Lucio Friedman was talking about, the bone structure this morning, fantastic work. I mean, all of it. There's so much excitement, and particularly here in Europe, I mean, where there's been a good investment in the science and the technology. I mean, it's amazing how much incredible stuff, the fast magic angle spinning, where that is leading right now, the membrane protein things that they're starting to do. I mean, it's fantastic. I think the field is very alive and vibrant. Well, again, I mean, that is an important question, really, and a question that I get asked quite a bit in the US in particular, because with the advances that are being made in recent years, in particular in cryo-electron microscopy, the question sort of is, why do you still need NMR? And crystallographers doing a great job, have done a great job. I think now is actually becoming the time where NMR can shine, at least in the biological area, better than it has in the past 20 years, because it's the ideal complement to both crystallography and cryo-EM, because we can fill in the missing gaps. So it's nice to see structures, but you want to understand how they work. You want to see what moves first, what moves second, what is the time scale that it moves. So what happens to those structures? All the rest, it's static pictures lead and give rise to a lot of speculation, and I think we can fill in the gaps in between. Now, it's perhaps not as prestigious as de novo structure determination, and NMR can do that, but that's obviously not where its main future is going to be, because it's a lot of hard work, and it remains a lot of hard work to work on any protein that's larger than 200 residues. In chemistry, I foresee that there will be some nice new experiments. I'm not going to let the cat out of the bag yet, but even there, for conventional chemistry, I foresee that there's going to be some nice new additions that people haven't been aware of. So the field is doing well, and there's a bright future. So I'm quite optimistic, and the new developments, particularly cryo-EM, is not making us obsolete. I think, by contrast, actually, it's making us more relevant by being able to answer then the questions that are being raised by the technology.